let's start. Okay, I'm resuming recording, right? Uh, Seems we have very few students right now, right? Or am I not seeing everyone here?
I think Eric said that he would not be able to make it to lecture today.
I see. Okay, okay. All right. How about Dylan and Helena? Any other word on them?
I did not speak to either of the two of them.
Okay, no worries. Okay, so guys, I think we are posting now videos also on YouTube, just because I think it seems that some of you have a hard time accessing the videos on Canvas. Is that true, or are you guys okay with Canvas?
I use the website. I don't use Canvas because it's very unstable.
Okay, what is unstable in Canvas?
Like the UI is very unstable. Sometimes it shows up, sometimes it doesn't show up. So I have to keep refreshing the page.
Okay. How about the web page which we have and where it's essentially using same Kaltra platform, but
I think
those
that's
work.
more stable than Canvas.
I see. Okay,
Yeah.
I see. Okay, so we'll keep posting then. I think we haven't posted recent lectures on that. Okay, we'll keep posting those on our website as well. Okay, thank you for that feedback. Um, any other comments, Renji, Puneet, on accessibility of the material?
Oh, it's fine for me.
Yeah, it's fine.
Okay, good. All right. So I think if you have any feedback on audio quality and all those things also, we'll be happy to take into those into account. Okay. All right. So let's start. Okay. It took 2 minutes extra, but okay, let's start. So today's class is basically how do we get breathing and heart rate. Okay. So midterm is finalizing towards May 15th. Okay. So if you guys haven't participated in the poll, I think make sure to participate. The idea of the poll is to identify the dates you can absolutely not make. Okay. Right. Um, Having preference is fine, but I think choose the way it's essentially um, like you absolutely cannot make it for some odd reason. Okay. Right. Okay. That's how you should fill this survey out. So I think I just want to quickly summarize the topic we'll cover up to the midterm, right? I think we'll cover today, or I think in general, like this is the set of topics at least we want to have for sure for midterm, right? Okay. We'll have breathing and heart rate formulation via across FFT windows, right? We'll try to show you techniques to eliminate static multipath, right? And we'll also kind of build an idea of identifying which bin has a person and which bin is just a stationary multipath or not changing multipath, right? Some of those things, or something which is changing much faster than the breathing and heart rate, for example. Okay. So that would be kind of the gist of it. Okay. So those all topics would be potentially covered before your midterm, right? Okay. And maybe dynamic multipath, we are not yet sure, just to give you context of what to expect, right? So let's recap a little bit, okay, where we left off, right? Okay. So in this recap, let's understand this, right, a little bit, right? H of t, right? Let me explain the architecture, right? You have a transmitter, okay, which is transmitting this FMCW waveform, right? X of t, right? Okay. That signal reflects back, comes to the receiver. You do a multiplication, mixing, right? Do a high pass filter with a beta thresholding, right? Okay. Where essentially you block all the strong reflections which are with frequency less than beta, okay, right? And we pass that through an ADC. My apologies here, right? Okay. This signal is more, I don't know what happened here. Okay. It should be H of t is here, right? This is H of NTS, okay, based on the sampling rate Fs here, okay, right? And then you can take FFT or some variant of FFT to understand a specific operation, right? Uh, just to recap, right? If you take H of t times this formulation, right, K tau t, right, okay, right, the expected outcome Fk tau can be written as, what can be Fk tau written as? Anyone want to take a guess first? If you do this integration of ht, right, okay, so h of t is nothing but all these negative exponents, right? By doing this integration with a positive exponent, right, okay, this positive exponent integration here, right, okay, what you would end up having here really is basically this integration will lead to terms which are basically, anyone want to take a guess first quickly? Those will lead to the terms which are Keshav or anyone else. So let's take an example. Okay, let's plot this first quickly. Okay, the idea is that once you take this kind of FFT, right? Okay, on x-axis you have frequency of k tau, right? Okay, for the signals where it exists, right? You will take something like, it will look like this, right? With a sync shape, a little bit like, okay, right? And as we have discussed this sync shape in past many times, okay, right? So basically this is, let's say, a specific tau value, right? For which a reflection falls back or comes back, right? And that's what you will get here, right? Now, this f of k tau, right? Okay, is nothing but, you can write in some ways, right? Okay, is, somebody want to try this, what it looks like? So what does happen to this exponent? This exponent goes away and gets replaced by a delta function or sync function in this case. Okay, so you will get ai exponent of j2 pi f naught tau I, right? Okay, that's because it's a fixed phase component, right? It's not changing as a function of time, right? The only thing which is changing with the function of time will get balanced out by this integration here. Okay, everyone following me here? So
Professor,
ideally,
I think I didn't follow that part.
okay, that's fine. That's a good idea. Thank you for asking that question then now. So when you multiply this negative exponent here, right, Keshav, with the positive exponent, right? Okay, correct. What you will be left with is tau minus tau I, correct? Okay.
Right.
So whenever, like when you do this integration, right, like we can kind of like write down this more specifically, right? Let me write down this integration more clearly, right? That way it's nicer. Okay. Sorry, just a second. Okay. So so if you think about it, so first I think this is what your h of t looks like, right? Okay. Okay, right? When you do h of t, when you take h of t, right, and do exponent of plus j2 pi k tau t, right, integration, right? Okay, what you essentially have is basically this component, right, gets involved with this, right? So you have k tau minus tau I into t, right? I'm just substituting h of t value into this expression here, right?
Right.
And
And you
that will
still
lead
have
to
the
ai exponent of minus j2 pi f naught tau I, right? But this is a constant term, okay? So it goes out of the integration, right? Okay. So what will this lead to if integrated from 0 to capital T? Let's say if it were integrated from minus infinity to plus infinity, what does this lead?
it's basically the exponential divided by 2 pi k tau minus tau I.
Yes. So basically infinite integration of this leads to this one, okay? Right? Okay. Correct? If T were infinity, right? And like, let's say this 0 were minus infinity, right? In that case, you will lead to this, right? Multiplied with ai exponent of minus j2 pi f naught tau I, correct? Right? But because we have finite time, right? This leads to ai exponent of minus j2 pi f naught tau I, right? Sync of kt minus tau I, right? Okay. with expression limiting it to
0 to t.
1 over t basically, yeah, because it's sync b tau, okay, generally, okay. So this will be like this, okay. It's basically, so if something is measured for a time period of t, right, that process essentially leads to sync of b t minus tau I generally, okay, right, okay. Here b is, what is b? B is 1 over
A
t,
tau.
1 over t, right? Okay, so it's basically, hopefully you guys get the fact that this will be sync of kt, okay, capital T, okay, which is the total time of the process, okay. It's fine. I think it's a math here a little bit more than actual intuition, right? But really the idea is that get the fact that this will be this kind of formulation when you do integration, right? Okay. More specifically, right, to the point is that this will be for each path. For each path, the amplitude, this is essentially showing the sync shape here, okay, right? And more importantly, this amplitude here is essentially more like a tau, which is essentially ai into exponent of j 2 pi f naught tau I, right? Okay. Okay. All right. Everyone with me on this front? Okay. Um, how about Puneet?
Yeah.
So now, similarly, when you do discrete version of this, right, summation, right? Okay, you kind of can first write down and start from h of nts. Okay, so quickly, just to make sure we are following a little bit more rigorously here, h of nts can be written as well as um, summation of ai exponent of j minus j 2 pi f naught tau I, right, times exponent of minus j 2 pi k tau I into nts. Okay, and you can do the same formulation and get to the same expressions which we got, right? So finally what you will end up getting, right, is something like if you take summation of h of nts, right, with exponent of positive j2 pi k tau nts, okay, this is your function f k tau, okay, right, okay, you will end up with similar expressions as we discussed, right? And you guys can evaluate this for yourself, right? But the insight really I want you to draw is following. This will also look like a sync, right? And its amplitude, Keshav, with me on this, or
Yeah, I'm following right now.
yeah. So the amplitude and all those properties will remain the same, okay? Right? Just it's a sampled version of the same signal, right? The same thing will hold for this as well, right? And you guys can derive that. Okay. So now let's go back to more intuitive, insightful things, right? Okay. So what we understood, right? Okay, that resolution, right, independent of sampling is 1 over b for time. Okay, right? Okay, correct, Keshav?
Yeah.
And so what it means really is that let's talk about resolution. Okay, of time is 1 over b, right? Okay. However, for distance, this resolution translates into it translates into Keshav, because it's 2d over c, right? Okay, which is proportional to 1 over b, right? It essentially means that distance has c over 2b as resolution, right? Okay. So what resolution says is basically that if there are two reflections which are coming back, right? Okay, at d1 and d2, okay, right? When can we separate them? That's the question it's asking or answering rather. Okay, separation. Okay, to be clear here. Okay, how about range? Range, as we discussed last time, right? What is it proportional to, guys? N over B, right? How does this formulation comes into play? The idea really here is that we take into account, so as we understand that FMC is a W wave, right? It keeps increasing frequency over time, right? Okay, let's say this is your T time, right? T, capital T. As you get more samples on this x-axis, right? Okay, what is your ADC doing? Your ADC is taking this received signal, which may be like, let's say, consists of multiple signals here, right? Okay, your ADC is multiplying this with x star of, before ADC you multiply this with x star of T, and essentially you're trying to measure the shift, right? And you kind of, what we intuitively understood is that you essentially are trying to sample multiple wavelength by sampling at different ADC points, correct? Right? So as we sample at more and more points, right? Okay, we kind of increase the range, as we have been discussing this even with the multi-tone setup, right? Okay. So why does it increases the range? Let's understand that. Anyone want to provide some insights? Ideas, Keshav? How do we intuitively get to range?
I think it's because it's related to P and then the time period we're sampling, right? So if you're sampling for longer, then you should technically get a larger range.
So you should get range equivalent to 1 over T, first of all, right? Okay. But again, depends upon the number of points you sample, right? Okay. So let's start with the resolution, right? Our resolution and time is 1 over B, right? Okay. So one way to think about this is like, I think the easy way to think about my resolution is this, right? Okay. And how many samples do I get in each period? Okay. Right. So you can take this as T over TS. Okay. Right. Because those are the number of samples you get in each time period, right? That's how much you can measure in length, right? Okay. So I already know resolution, right? Which is like, when can I separate these two when they can be in two different bins, okay? Right? This is the closest distance two things can be, right? Okay. And how long can we measure? How long can we measure is basically how many such separations I can create, right? So the way to think about it is T over TS times 1 over the resolution, right? The number of points, okay? Does it help you guys in some ways, Keshav? Is it
Yeah.
easy to think? Okay. How about Puneet? Is that most intuitive way? I think, yeah, for me, it just boils down that FFT is the way to do it. Okay. But Puneet, go ahead.
Mostly, I think from the frequency bin perspective, like the smaller frequency bins we have, the larger will be range in time domain. That way I think
So
about
this
it.
is the bin, right? Bin size, basically.
Yeah, yeah.
Right. And then basically the range is that number of bins times the range. Correct. Right. Okay. So that's N over B. Okay. Right. And this leads to, now let's talk about distance, right? Distance is again 2D over C, right? Okay. N over B, right? So what it really means is that it will be, the resolution for D will be C over
2B times N.
N, right? Okay. Basically, because it's two-way, the range has decreased for some extent if you think about that way. Okay. Right. So I think briefly we understand this multi-wavelength intuition, right? Because we have been studying with one wavelength, two wavelength, and whatnot, right? Okay. So tell me, guys, following, right? Does it matter in order to measure breathing and heart rate, the range and resolutions of the FMCW?
Can you repeat your question, Professor?
Does it matter that in order to like get breathing and heart rate for one person, right? Okay. Does these range and resolutions matter? So recall our first class, right? Or first or second class, where we showed that even with one frequency, I can get you breathing and heart rate, right? Okay. Just that I need it to be super accurate, right? So what I'm trying to say is that following, right? We understand this multiple wavelength, right? We understand formulation of distance, right? This is your summation of h of nts formulation, right? With exponent of plus j2 pi k tau nts, okay, right? Okay. So I think the point I want to make is that third point here, right, is beyond these two is accuracy, okay, range resolution and accuracy, okay. So even with one wavelength, you can get breathing and heart rate, okay. It just, you won't be robust enough. And we calculated in one of the classes that 1.5 gigahertz is the right frequency, okay, right, to capture both breathing and heart rate, right, okay. That it will be done in one wave of this 1.5 gigahertz, right? Anything lower than this will be okay, right? Even above this, we said that we can make it work. We just need to do some continuity of phase, right? Okay, right? We'll come back and connect this dot, okay? So the point I'm trying to make is that these range and resolutions are good, right? But they are for different reason. They are for making it robust, less to do with basically how you wanna, or can you even get breathing or heart rate, right? So that gives us the formulation of distance with FMCW. That's what we have discussed, right? And then we know range and resolution, right? Okay. And now, finally, let me make one more point, right? Which is the FFT based formulation, right? Which is essentially like this formulation, right? Okay. So is this FFT first of all? Keshav?
It looks like it.
Right. It's actually, let's call it DTFT rather. It's DTFT, not FFT. Okay. Right. And we know because it's like this time version is continuous. Okay. Right. So that's why it's DTFT, not as such FFT. Okay. Right. Discrete time Fourier transform. And it's, you can call it inverse, but it's Fourier transform, right? Okay. So the problem with DTFT will be that following. You will measure f at k tau at some discrete points. Let's say k, tau k's. Okay, right? Does that make sense?
Are the two Ks the same?
Which case? Sorry. Oh, my
So
bad. No, my bad. Let me use a different notation. Sorry. Yeah. Thank you for making this aware of this. Tau m. Okay. Right. Now, can you tell me where this tau m goes from 0 to what value? Meanwhile, I'll complete the expression here. How about Puneet? How about you tell us what tau m goes from where to where?
Now is 2D over C, right?
Sorry?
Now is 2D over C. So
No, that's, sorry, 2D over?
C.
That doesn't make sense. It's nothing to do with 2D over C. Tau m, I'm asking where does this tau m goes from, what points? So it's essentially like taking DTFT and evaluating at fixed number of points, right? That's FFT. What is FFT? FFT is like DTFT evaluated at some fixed frequencies, okay? Call them FM here, okay? Right? Okay. So similarly, this FM is the frequency here if you think about it, right? Let me write down this as tau m, okay? Subscript m, okay? Everyone follow? Keshav?
yeah.
What will be the maximum value of tau m? Can anyone tell me here?
Would it be T, the time period?
No. What is resolution and what is range? So what is range, Keshav? 1 over
N over B.
right? That is what it will be. Okay. Does this make sense to everyone? What will be the separation between two tau m values? Puneet.
1 over B.
Yep. Does it make sense now, guys?
Yeah.
Keshav?
Yeah.
So between two bins of tau 1, let's say tau 1 and tau 2, right? The separation will be 1 over B. Okay. Or not C over 2B rather, or 1 over B rather, because it's tau. Sorry. Yeah. Okay. Everyone with me?
Yes.
Okay. So this generally builds the construct for you to how to think about this DTFT within a discrete time with FFTs. Okay. Right. So now I think what we'll do is we'll use this transform today and essentially learn how to get breathing and heart rate. Okay. Right. Okay. And like start from the application layer again. Right. Okay. And this is not just limited to breathing and heart rate, right? You can, sorry, Keshav, you had asked T. What is T? Oh, this is for older message or this is just now?
Oh, this was me trying to answer that question.
Okay, okay.
Yeah.
Good. Yeah, sorry. Yeah, I was not noticing the chat so far. Sorry. Yeah, let's continue. So basically breathing and heart rate variation, right? Okay. And like understanding application level specification and then boiling down to the FMCW parameters, waveform parameters, right? And using them to identify breathing and heart rate, right? And finally, one of the most important thing with the FMCW, which is quite overlooked, is like looking at the phase information. Okay, right? And then I will finally connect back with some of the first few lectures we kind of have been looking at how to go about them. Okay, right? So let's understand, right? Breathing and heart rate, right? Okay. Breathing signal so far we have been assuming that it will be like 10 centimeter. Again, this is peak to peak. Okay, right? Is that's what we have been using, right? Okay. And for heart rate, we have been using 1 mm, correct? I need to check these parameters, but okay, assuming that this is this parameter and the spec we are trying to design this for, right? Okay. So more than that, right? What is interesting with breathing is that breathing changes with time, with what frequency? Keshav?
I think it was around
0.2 to 0.4.
yeah.
0.2 hertz. Okay. Let's take 12 breaths per minute, BPM. Okay. Right. And for heart rate, it is
0.6.
0.6.
yep. Somewhere between 1.5, right? Or let's take, what is a standard popular example you guys keep using? Come on, folks. It's
0.6.
yes. What is the breathe per minute? Let's take 60 breathing per minute, okay, or beats per minute. We'll make it 1 hertz for now, okay. I think that's let's keep to that example, okay, right? So with FMCW, right? Okay. Now these are our specifications, right? Okay, right. What does this translates to? Okay. What it translates to is that D is changing with 1 hertz, right? We need to at least, or let's call it like at least try to measure the sampling rate should be at least how many samples, guys, to measure heart rate accurately for 2 hertz, right? Okay. So what I'm saying is that let's say D of T, right? Okay, which is your D0, right? Plus DH times sine of this, right? dB times sine of this and dH times sine of FP, FH frequency of breathing and frequency of heart rate, correct, right? So this D needs to be measured at least at 2 hertz rate, correct, right? Now, with your previous way of doing FMCW, right? What is your sampling rate? How often do you get a D? And this is one of the questions somebody also has asked on Piazza, right? Okay. So in a way, when we take this FFT, guys, okay, we assume for this small period of time, right, from the time of 0 to capital T, okay, right, okay, the environment is stationary, correct? Everyone with me on this?
Yes.
Thank you, Puneet. Yeah. So now, what is the rate at which we are getting samples for D? Keshav. Is it T? So you get one sample for every T seconds, right? Every T time, yeah, you get one sample, right? Okay. And what I mean by one sample is that essentially you get one measurement of D, correct? So think of this from following point of view. You're calculating this f of k tau m, right? Okay. That's essentially like for this entire period of 0 to capital T, right? Okay. I'm giving you the output of the FFT, okay, which will look like this, right? Which will give you that there is one strong component at this distance, right? Okay. More specifically, right? Okay, let me write this down, okay? So let's take an example, right? So from 0 to capital T time, right? You got one F tau, okay? Right, Keshav? And let me just draw this as a third dimension here, okay? For next time from T to 2T, correct? Okay. Let me write T here, okay? From T to 2T, right? Okay. You have another similar function, right? Okay. Which measures T distance, okay? So each snapshot gives you a measurement of T. It's the same as your two-stage process, okay? So just to iterate and just to connect the dot back with the original thing, right? Okay. Take a look at this architecture we have drawn earlier on. Okay, let me just pull that architecture up quickly here, okay, and copy it over. Is it still visible, right? I'm not going to write the mathematical expressions here, right? But just to give you a sense, right? Okay. So here you calculate f of k. What do you calculate? K tau m, right? Okay. Think of this block here as.
Professor, I have a quick question.
Go ahead. Go ahead. Yeah.
So in the formulation of the summation earlier, we noted that tau m goes from 0 to n over b.
Mm-hmm.
But in the summation you wrote, it goes from 0 to t. Was that correct?
It's still correct. Okay. Let me explain. Okay. So let's see. I think it's a matter of, in this case, for example, right? NTS needs to start from 0 and it goes all the way up to T, right? Okay. What is T? When you take, it's equal to capital N, right? Correct. T over TS is nothing but capital N, right? So you can say this summation goes from 0 to N, for example, right? Okay. Is that the question?
I'm still a little bit confused as to why it goes.
Okay. Confused for with expression. Let me, why don't
So
you tell?
the same expression that we were talking about just now.
Right.
So
Okay.
aren't we summing over all tau m?
No. We are summing over. Oh, sorry. That's a good question. Thank you for asking this. Okay. We are summing over n here, guys. Okay. If everyone is not clear, look, it's the time index on which we are summing or integrating. Okay. Right. Okay. So think of this. This is your equivalent of time index. T equals to NTS. Okay. Right.
I
It's
see.
summed over time, guys. Okay. Not over summed over n comma t. Okay. Depending upon the notation. Right. For example, right. For this integration here we talked about in the continuous time. Okay. It's summed here for what, Keshav?
T,
Yep. T from 0 to capital
capital T.
T. Okay. The same thing in digital domain basically becomes this summation here, for example, goes for some n equals to 0 to capital M. Okay. Does that make sense now?
Yeah, that makes sense now.
Thank you for asking these questions. I think these are good questions and keep asking them, okay, whenever you feel like it's not clear. Okay. So now you understand this three-dimensional notation, right, Keshav? And everyone else here?
I have a doubt, like
Go
similar
ahead.
to in multitone also. When we take at one time period, I understand we'll get a sync functions. Like we'll find the dominant path, and
Right,
we do it for multiple time instances.
right.
But I see since the resolution for distances will be pretty bad because I calculated, and for 1.5 gigahertz also, it will be 1 by b, right? And so
Yeah.
so it will be come around in meters. So we will not see a change in the across time in the distance variation. It will be the same bin where we'll see the peak always.
Right. So that's good point, right? Okay. In the 1.5 gigahertz, definitely that's the case, and that's not the way to analyze it. Okay. And this is where I think you need to step away from resolution. And this is the point I made earlier on, right? To measure breathing and heart rate, you don't need any range or resolution, by the way. Okay. You only need accuracy. Okay. Just because I can track the phase as it changes, right? So, for example, here as well, right? What is the phase here, by the way, guys? The phase is proportional to A tau, right? Correct? What is A tau? Exponent of J 2 pi F naught tau I. Okay. So what I'm trying to say, Puneet, is following. The peak won't change. Okay. But its phase will change. Okay. For your one tone, by the way. Okay. In this case, for breathing, the peak will change. Okay. And for heart rate, the peak won't change. And we'll go over this slowly in this today's class, and hopefully that will clarify for you. Okay. But just connecting the dots, right? The first stage process gives you, does that answers your question, or at least at a high level tries to give you a sense of the answer to the question, Puneet?
So I'm still not sure. Like I know the where
How
my
about
peak is, the
we
distance.
take this question towards the end of this class, and hopefully
Sure,
this will be
sure,
clear. Yeah.
sure, sure.
Yeah. So once you have this f of k tau m, right, for time instance from 0 to t, right? Okay. Let's call them f of k tau m at time 0. Okay. Then f of k tau m, right, at time t, right? So this is basically your the first row I'm drawing here, or the first foremost thing, right? This is nothing but f of k tau m, right? 0, this one. How about this one, Keshav? This is f of k tau m, comma, what is this one?
T is a capital T.
T. Yeah. So basically what we are doing is that for every time, for every one chirp which goes from 0 to t, right? Okay, we get one FFT output, correct? Okay, that gives you f of tau m at 0, f of tau m at t, and then so on and so forth, right? From t to 2t, that's another chirp, right? Okay, from 2t to 3t, there is another chirp, right? Okay, right. So do you understand this two-stage process? The first stage process is, you can say, estimate. Now this can be equivalently said as f. Okay, instead of calling h hat, I'm going to call it now f, right? Okay, or more specifically, you can call it fd or fk tau m, as you like. Okay, right? So that's first stage of the process, right? What is the second stage of the process, Keshav? The second stage of the process is to take, let me,
We do estimate for multiple chirps.
I think that's already, we kind of explained that f of d comma tau m like is 1 for each chirp, right? Okay. Yes, you're correct that we'll now analyze it for multiple chirps, right? So just to clear and complete this thought process, right? Okay. Again, I'm going to copy this. Okay. So now this f of k tau, right? How can I write this now? Let me write some notation, right? I'm going to write f of k tau, comma, capital N times t, okay? Or let me write it as m, sorry. No, m I already have used. Let's call it L. We can use it for L. Doppler is L for me always. Yes, okay. All right. So we'll use L, okay? So it's L times capital T, correct? This is fed into the second process of the part of the process. Right? And this second part of the process, by the way, guys, right? Okay. So this is essentially generating one for each chirp, by the way, right? Fk tau LT is like for one chirp each, right? Or Lth chirp, let's call it Lth chirp. Does everyone understand by chirp? I mean this FMCW transmission and the entire process of FFT, okay, right? So this signal then is fed into, what is it fed into? Measure breathing and heart rate here, okay, right? Or what we call here is more like analyze time series, like we have been calling this previously. Or now, is this clear, the process, right? At a high level, the process is clear. Now, how do we go about this process is a more important and interesting question, right? Puneet, make sense?
Yeah.
Keshav?
Yeah.
Okay. So one trick will be like, as we discussed, right? We'll just monitor what happens. Let me just explain here. Let me highlight. Let's see, for example, I analyze. Can you see the highlight here? I guess yellow color
Yes.
is not visible. Or let's orange. Okay. So we'll essentially use these times and their peaks and see the peak shift, for example, right? So let's take an example from our previous parameters, right? In the last class, we defined a radar which had 5 gigahertz as F naught, okay, right? 2 gigahertz of B, right? Okay. And I don't think we need anything other than this, right? And this will give us resolution of D as how much, guys? C over 2B, which essentially comes down to be 7.5 centimeter, correct?
Professor, aren't you multiplying that by n?
No, this is resolution. What do you mean by
Resolution.
not
Oh,
resolution?
sorry,
Yeah.
sorry. Yeah.
So, and what was capital T in last class? I think we took it as 100 nanosecond or something like that. Okay, right? So now think about what is the sampling rate at this point, guys? The sampling rate at this point is T, right? You get one sample every time T, right? Okay. Correct, Keshav?
Yeah.
So in a time series, if I get one sample at time T, right? Every next sample comes at after time T, right? So let's start from this part, right? What is the process we are trying to measure? We are trying to measure 1 hertz heart rate, okay, here, right? Okay, with amplitude of 1 mm, right? and 10 centimeter with 0.2 hertz breathing rate, right? Okay. What are the implications of these two process on this side? Okay. So let's start with the frequency implication. The frequency implication is that this T should be at least 2 hertz, right? Okay. Let's say more like it's because it's time, right? Or let me erase this a little bit, right? Okay. Let me call 1 over T should be greater than 2 hertz. Okay. Does that make sense, Keshav?
Yeah.
Now, similarly, this 1 mm and 10 centimeter, right? Okay. How can we derive some insights from this, right? So let's understand what is the bin width here. Okay. Meaning, when I take f of k tau m, right? Okay. Right. How much is each bin separated from the other bin, right? So basically, when you do f of k tau m, right, it will be like bunch of these discrete signals with x-axis as tau, k tau, right? Okay. And let me just draw maybe more like a sink, right? Yeah, it doesn't look like sink, but it is sink, let's say. Okay. Let me redraw. Let's say this is your sink, right? I get one sample here, one sample here, right? Different k tau m's, right? Does that make sense, Keshav?
Yeah.
So now, basically, right, with breathing, because your this bin width is 7.5 centimeter, right? Okay. What would happen really here is that when you try to process this data, right? And let's take an example that this is your, I'm representing f of k tau m here, okay, at time instance 0, okay. So let's say you see a peak here at this bin, okay, right? And more or let's say it's like the highest peak, okay. In the next time instance, right, okay, you'll see the same peak here somewhere, right, okay. But at some point, right, okay, so let's see what is that point, right? So let's say your breathing is 2 hertz, right? What it means is that this is your D, by the way, axis as well, correct? So because breathing is changing slowly, right? You'll see some kind of a sinusoid pattern here, okay, right? Does that make sense? Between this D?
Yeah, it's because you have different chirps, right?
Yes. At different chirp, your D will change slowly, right? Okay. But just to give you a sense, right? Because we are doing every capital T was 100 nanosecond, right? So you're getting how many samples? What is your sampling rate here? 1 over T will become more like 10 megahertz. Okay. Right. Correct. Which is like a whole lot more. Okay. But the idea really is that this D distance will change after 10 million samples, right? Okay. Or everyone following me here?
Yes. Professor, but that distance bin of 7.5 centimeter, isn't that a little bit too large for the other metric? I think this is for heartbeat.
No. 7.5 meter. This is for breathing. Sorry, breathing, right? So let me just maybe quickly correct a few things on the slide. Okay, this is centimeter. Okay. Sorry, for breathing, we need 10 centimeter, right? Okay, so you guys understand that breathing, we can get it, right? Okay.
Yeah.
But we don't know how to get heart rate now.
That was my question. Like, isn't that too large for the heart rate binning?
Yes. For heart rate, you cannot separate the bins, right? And does it make sense to Puneet as well?
Yes.
Okay. Let me. Sorry?
I mean, is this still too large for breathing?
Which plot? Sorry.
I mean, 7.5 centimeter.
Yes, yes, yes.
Yeah, just a changing between two beams, or three beams at most.
Yes, exactly. So even for breathing, there are not many levels. Is that what you're saying, Renji?
Yeah.
Yeah. So even for breathing, right, you don't have that many levels as such. Okay. Let me erase this a little bit, right? Okay. And let's draw first distance. Okay. Right. Here on the right side. Okay. I'm going to draw distance here, but let me explain. Okay. On y-axis, I have time here. Okay. And breathing changes here. Okay. So this is your D naught. Okay. Let's call it this your DH or D breathing by 2. And this is D minus breathing by 2. Okay. So, and let's say this is your time here is, let's say 2.5 seconds. Okay. Just because like breathing is 5 hertz, let's say. Okay. Right. Right. So what would happen really, guys, is following, right? In this entire 2.5, right? Here, when you look at this f of tau here, right? Okay. It will maybe shift by 1 bin here. Okay. Not even 1 bin. Okay. But let's say that's basically the maximum shift you will see, right? Okay. Does that make sense?
Yes.
Sorry, I kind of have turned up the zoom weirdly. I don't think you guys can see it. Okay, yeah, sorry. Yeah, next, I think when you go back to this 5-second time point, okay, here, right? Okay. Then this maybe will go back to the original bin. Okay. So you'll barely see a fluctuation between like 2 bins. Okay. Right. So how do you measure with just small fluctuation between these 2 bins? Okay. Right. Does that make sense, Ranji, Keshav?
Yeah.
How about you guys give me a crude algorithm? So now we understand overall problem statement. Okay. Right. So let me summarize few things. Okay. Capital T, right? Here we have, this is more than sufficient. Okay. This is like your 10 megahertz. Okay. What you really need is just even something which is as slow as like a few kilohertz is good enough, right? Or more specifically, 2 hertz is sufficient, right? 2 to 3 hertz is sufficient. Okay. That's number one. Okay. So this is like super over specified parameter. But bandwidth, super under specified. Correct? Or it looks like it is super under specified. Sorry guys, I think I just got a warning for my laptop running out of battery. Give me a second, I'll get my charger. Sorry, yeah. So bandwidth is very little because it gives you 7.5 centimeter resolution. Okay, would have loved to have some millimeter resolution. Okay, right. Now I think what I'm going to show you today is that these parameters which may look you insufficient are actually sufficient. Okay, so that is the objective function which I have in next. So we understand that FFT based technique is a little bit flawed because of its binning culture. Okay, right. What is a fundamental flaw? Can someone tell me what is the flaw with the go ahead. Somebody want to tell me the flaw in our algorithm right now here? Keshav? So if I were to draw the time domain diagram here as output of this, okay, what I will see is I'll see D is like 1, and it's going to be in one bin for majority of time, then goes into the other bin and comes back. Okay. So just to give you an example, right? It is goes to this, comes to this bin, right? And this maintains in this bin and then goes back to this bin, right? So essentially you'll see like some kind of a square wave, okay, if you may, right? Everyone following this?
Yeah.
Okay. Puneet?
Yeah. Yeah. Actually, we are seeing which bin we are in. So it's a square. Yeah.
Yeah. Okay. So the problem is we are not seeing this continuous wave. We are seeing a square wave. Okay. That is the problem. How do we make this square wave into more continuous wave? Correct?
Mm.
Does that make sense? Keshav, to you
Professor,
as well?
why do we care about it to be continuous though? Like even if it is square, you can still get the frequency, right?
So this is where I'm gonna now explain you a more important fact. The problem is right now the world of wireless, right? Okay. Sorry. Right now the world of wireless, as we know, right? If you can only measure beats per minute, okay, that's a very bad metric, because let me explain. Some breathing and heart rate conditions are required to measure some variation, right, beyond just breathing and heart rate. What I mean by variation is that if somebody has a double beat, okay, that is something called as cardiomyopathy or something like that. I'm not sure about exact disease, but if your heart has a double beat very fast, very quickly, such double beats are sometimes hard to decipher, okay, right? And if you don't have resolution on this side, right, you essentially cannot do more than just saying that if your breathing rate is X hertz or Y hertz. Okay. As we know, even breathing changes from 12 to 25 hertz. Okay. Right. Or 12 to beat 12 to 25 beats per minute. Okay. So really, in order to get more particularly medically informative information, right, we need to kind of get better understanding of how to get this more accurately. Okay. Hopefully that answers and addresses your question.
Yeah.
So now let's look at an algorithm right now. Okay. The problem we have is that discretization. Okay. Right. Okay. What I'm trying to rather say here is that let's say your underlying 2D over C, right? This is your K tau M, by the way, K tau 1, K tau 2, right? All the way up to K tau M, right? This is the D axis or K tau axis of your F of D, okay? Right? Or F of K tau.
Professor, I don't think we're saying anything.
Yeah,
Oh, sorry.
it is.
Yeah. Thank you for informing me. Yeah. I have to reshare. Can you see it now? So x-axis is really tau here, K tau, right? And this is your output of your FFT, right? And let's say the actual underlying 2D over C, right, falls between two taus, okay? K taus, 2K tau, K and K tau, K plus 1, right? Okay. So this is your underlying reflection, right? What would happen is that because it creates a sink shape, right? Okay. As we have discussed, you'll get some kind of this as your sink, okay? This is, I'm plotting the amplitude here, okay? So you'll get some kind of this behavior, right? Okay, right. Ideally, you would like to reconstruct this point, right? Correct? Can we reconstruct this point, guys? I think somebody from Renji, maybe from your end, there is some noise coming. If you can mute yourself, that would.
Oh, yeah.
Sorry. So, yeah, what was I saying? How can I make it more continuous instead of discretization of the bin? Ideas? Puneet, Keshav? Think, guys, think. So the idea really here is that first, right, you identify that there is a square pattern whose frequency is somewhere between less than 1 hertz, okay, 1 to 2 hertz, okay, right, okay. Identify those bins, right, or the areas of those bins, right. Next thing, what would you do if you were given this problem to solve? Let's think from first principles, right, okay. So why did I introduce FFT, Keshav? It's just because it's simple to compute, right, okay. Instead, can I do DTFT or can I do an FFT where I have more points here instead of the number of points which are fixed, right? What if I have more points here on this axis here, right? Wouldn't that make my job simpler, right? As in, like, I would not get the square waveform. I would get more levels, right, in this waveform, right? Like, I would get like more levels because I can measure this distance more finely, correct? Does that make sense to everyone? The idea here? Keshav, Puneet? Puneet? I don't hear you, I think.
Yes.
Okay.
Yeah. It's like we are trying to increase the resolution in distance
Yes.
domain.
Yes, exactly. So the idea really is that we narrow down to a zone of distance, right? Okay. And in this that distance, right, you compute f of k tau, right, more finely. Okay, right? You take from tau k to tau k plus 1, right? Okay. You can compute more points. Okay. Okay. So this is kind of an slightly off books algorithm, right? And not a lot of people use this algorithm, by the way. Okay. But this is essentially will give you much more accurate breathing. Okay. Right. So you essentially take this window of k tau k and tau k plus 1, right? And maybe split into, let's say, another 40 levels. Okay. Right. Okay. So you have k tau k plus delta, right? And so on and so forth. Okay. All the way up to k tau k plus 1. Right. Now, delta can be, let's say these now are number of points are, let's say, some capital M. Okay. Maybe R, capital R. Okay. Super resolution, some ways. Okay. R for resolution here. Okay. So in a way, you're kind of doing super resolution, guys, by the way. Okay. It's just a very simple technique, but it does some kind of super resolution algorithm here, right? So essentially you take tau k plus 1 minus tau k upon R as delta, right? And you compute this new. Now, to compute f of k tau, right? We know that, right? How to compute that using h of nts, right? For, let's say, k tau, any k tau k plus delta, right? Everyone clear on this? The formulation here we have exponent of minus j2 pi k tau nts, right? Summed over Keshav n, right? From 0 to capital N. So does this at least resolve or give you a hunch that, okay, yeah, with this technique, maybe we can do slightly better, right, for breathing? Puneet, convinced?
Yeah. Theoretically we can do, but how will we get these measurements? Like, still it's a
There are no new
function.
measurements. I'm just computing this same measurements of HNTS, but with more fine-grained FK tau. Okay, right?
Professor,
So
can you say again what R is?
R is nothing but just the number of points here. Yeah.
Oh, okay.
Sorry. Yeah. If that, yeah, R is just number of points here. And I'm just taking the window of tau k and tau k plus 1, right? And making it more fine-grained, right? Instead of 2 levels, I have many more levels now, right? Like I showed you in this figure here. Okay. Right. There will be now k levels instead of just the 2 levels. Okay.
I don't think that still answers Puneet's question, right? Like how are we
So
getting
this is
those?
where I'm trying to understand and maybe make a difference, right? Resolution is more to do with how to separate two signals or two reflections, right? Okay. But if one reflection is changing with time, right? That's nothing to do with resolution, guys. Okay. So that's the fundamental point I'm trying to make. Okay. Resolution is about two signals concurrently. Okay. What we are doing here is we have one reflection, okay, which is changing with time, right? So this is where resolution doesn't apply. When will resolution apply, Keshav? Resolution will apply when you have signals coming from, for example, two people in an environment, right? Okay, one is Keshav, one is Puneet, right? Then resolution will apply, okay? Which signal is Puneet, which signal is Keshav's, right? That's where resolution applies, okay? But if it's Keshav's signal only which is coming back, right? And it's changing slowly over time, right? And I'm trying to measure that slowly changing process over time, right? Then resolution doesn't apply. Puneet, go ahead. You tried unmuting yourself. I was wondering if you have a question here. And Keshav, even if you have
It got disconnected and reconnected again. So.
Oh wow, you got disconnected in a crucial time. But okay, Keshav.
So then, are you saying that in that square diagram plot that you drew, that even there's like a small variation where it's drifting to the right and to the left? Like it's not the
Yes.
exact same place of the bin.
Yes. So I think what I'm saying is that for resolution to matter, right? If there was another reflection which was coming here, right, at this point, let's say, okay, let me highlight this point, okay. Whether you can understand both their movements over time or not, that's where resolution matters, okay.
I see.
Keshav, Puneet, does it clarifies for you how? So this part of the process is more to do with accuracy and less to do with resolution or range for that matter here. Okay. Puneet, make sense?
Yeah, like calculation wise, it makes sense. I'm just thinking how it is actually will do
So
it.
I think this is a good example case where Ish will cover in his lab this week. Okay. Right. Renji, go ahead. You had a question? Yeah.
Yeah. So basically, at here, we are not directly doing FFT, right?
Yes, we are not doing
Or
FFT.
we are trying to first interpolate it and then do the FFT.
Yes. Yes. We are doing DTFT, and you can call it interpolate, or you can call it, however, there are many ways, right? You can call it super resolution, right? Because like I'm trying to identify where this peak is, right? By looking at these samples, I'm trying to identify the underlying observation, right? Okay. This is the underlying observation. It's also called as super resolution, right? Okay. Right. But I think for FMCW, you can view super resolution as the most simplest form like that. Okay. Right.
Professor, what happens if we do take the Fourier transform of that?
Of what?
Of the square waves, like it is
You'll
drifting.
see the heart rate. You'll get the rate. You'll get accurate breathing rate. Okay.
I see.
You won't be that you won't get the breathing rate. Okay. You can tell me variability of frequency, right? So if you're breathing, let's say at 12 hertz and then your breathing fastened because you were running or something like that. Okay. And it went to 25 breaths per minute, right? You can make those differences out even with a square wave. Okay. Right.
Right.
But when it comes to really like getting the more time dynamics, right? Particular time dynamics, right? For example, right? For a condition which is called as COPD, okay, right? It's like an asthma related problem, right? Okay. So I think there they try to measure flow volume. What is flow volume is that how deep your breath was and how deep and shallow the breath was, right? Okay. Now this is requires a subtle variation, right? So for example, right, your breathing Keshav can be 7 centimeter, DH can be 7 centimeter, DB can be DH 7 centimeter. For me, for example, the breathing can be 10 centimeter. Okay. All right. And what it just means is that I'm breathing very hard, right? Okay. As in I'm like taking a lot of air in and a lot of air out, right? And because of that, my compressions are higher, right? Or it can be just nothing to do with, it just could be something to do with our physiology, weight, and other things, right? I think this is something which you would like to measure, but you will be lost or miss this information if you don't apply such super resolution. Okay. All right. Okay. Now, even after applying this kind of super resolution, right, the question is, can you still get heart rate with this now? Okay. Right. Heart rate is 1 mm movement, right? 1 mm is a lot. Okay. So I think the best way to think about it is that what would 1 mm change? Okay. If a bin size is like maybe, so if a bin size is 7.5 centimeter, right? Okay. I need to split this, let's say, by a factor of at least 100, right? Okay. To get to at least 0.75 millimeter, right? Or close to 1 millimeter, right? Okay. So, and I think you should try this in your lab, right? Maybe it might work. Would be surprised if it works because of SNR, right? Limitation. You cannot, in a noiseless case, sure, you will get it to 1 millimeter as well, right? Noiseless case or noiseless world, this doesn't matter, right? But in the world of SNR, this will start to matter, okay, significantly. Actually, I was hoping, okay, let me make some interesting observation, okay? So after doing this, right, Keshav, right, let's say if I can smoothly track the peak at which the movements are taking place, right? Okay. Let me draw it, right? Okay. So after doing this super resolution, right? Okay. What I can do is I can do more fine-grained points here, right? Okay. And because of which I will get, let's say, you're breathing nicely with smoother variations. Okay. The problem is the heart rate is on top of this is like 1 mm variation, right? Okay. And because you have noise on your receiver, right? Okay. You cannot almost always accurately make sure that you get this. Okay. And this goes back to how much averaging and whatnot you need to do, right? And how much phase noise you have, right? Okay. But the idea really is we will go back here to the term on A tau, right? Okay. So this is essentially, think of this as your x-axis as tau, right? And y-axis as time t of your breathing, right? Okay. So A tau, remember the term A tau, right? What is A tau? So far, what we have been doing is that we are just trying to measure this peak, where this peak lies, right? And based on that, we are trying to identify the delay, right? Okay. But this peak also has some complex value, okay? And what is that complex value, guys? It's your A tau, right? Okay. Can someone tell me what A tau is? Keshav?
AI exponential of j to pi f naught tau.
Right. So what is the intuition, guys? Okay. Now let's take an example, right? We have done this F naught analysis, right? What is your F naught? 5 gigahertz, okay, right? Now, I have told you many times that I think for a good, reasonable receiver, right, measuring 6 degrees is totally fine. Okay, right, phase. So 5 gigahertz means, right, that for 360-degree, right, okay, on 5 gigahertz, how much time should pass? How much should be tau? I'm gonna pick on you, Keshav, again. 0.2 nanosecond, correct? In 0.2 nanosecond, you will get 360-degree phase rotation at 5 gigahertz, correct?
Right.
Now, if you were to get this 6 degree here, okay, right? Accuracy, okay, right, okay. Or you can say resolution for the receiver, but this is the resolution of receiver's phase measurement, okay. How much will that get you to? 0.2 over 60, okay, which is 0.02 divided by 6, or it's like we did this calculation, right? It was
0.03, 03.
Yeah, 33, okay, right? Which is 3 into 10 power minus 12 picoseconds, okay? Or 3 picoseconds, let's put it as 3 picoseconds, okay? Now, what is 3 picoseconds? It's like 30 centimeter divided by 1000, okay? 30 centimeter is for 1 nanosecond, okay? So this is essentially comes down to 0.03 millimeter actually, okay? So your breathing and heart rate are at 1 millimeter, correct? Sorry, heart rate is at 1 millimeter, right? So what I'm trying to say is that what I'm going to do next is I'm going to start measuring the phase, okay, of a tau, right? Okay. I'm not only going to just look at the amplitude or the bin here, right? But I'm going to also look at each bin, what is the phase value it has, okay? Is it clear or is it confusing, this phase?
So are we going to fix on one bin?
Are we going to do what from?
Just looking at one bin or keep changing?
So I think it doesn't matter actually in this case, okay? So you can keep changing the bin and identifying the right phase, okay? You'll still get similar performance actually, okay? And I think this is slightly more advanced topic, okay? But ideally what you would do is you will first find out this trajectory of your tau, okay, right? What tau values to go, right, as time increases, okay? Or for each slice of FFT chirp, right, or FMCW chirp, right, okay, what is the tau you should use, right? And for that each tau, then you can just measure the phase, okay? But turns out it doesn't matter actually, okay? And you will do this in the lab this week, right? Okay. And we'll kind of have a better sense of this. I think I was hoping I want to go cover the heart rate, but I will leave you with the intuition and we'll come back to next class and try to cover the heart rate quickly and then go on to the next topic, okay? Questions?